Hey everyone, so in today's video we're going to be looking at section 4.2, which looks at measures of dispersion. What does that mean? It's basically looking at how spread out our data is. Okay? There's a couple of ways that you can look at this. You can just look at it as though how spread out is all of our data, starting with the lowest point up to the highest point, so how spread out is the whole data set. Or you can look at how each data point is spread around the mean. Okay, remember the mean is kind of like a central value. It gives us an average of all of the data. So we can look at how spread out our data is from that one point, as opposed to just looking at the largest and smallest point and seeing how far they are away from one another. We're going to see how each data point is spread around that mean. Okay. So quick thing to start, that something that you've seen before and we have discussed it very quickly, is the range. Okay, this is a very obvious measure of dispersion. We're not looking at anything compared to the mean here. We are just looking at how far away are our largest and smallest data points. Okay, so the range is just the largest data value minus the smallest data value. Okay. Obviously, the larger the range, okay, that means that there's a bigger difference between your largest and smallest data value, so you would assume that your data is more spread out. The problem that we have with this is when you have outliers. Okay, if I have an outlier, just even one or two outliers, so if I have one outlier at the lower end and one outlier at the upper end, most of my data could still be really closely clustered around that mean. But with these outliers, the range is going to tell me that this data is really spread out. So for example, I could have, let's say, my data points were 1, 21, 25, 27, 28, and 79. Okay, I have 6 data points here. Now most of my data is clustered in the 20s here. Okay, most of my data is really close together, but I have these 2 outliers on either end, and my range would be 79 minus 1, which is 78. So this range is telling me that my data is really spread out, when in fact the majority of my data is actually clustered together. So that's why we don't really like using the range as a measure of dispersion, because in some of these cases it may not be a good measurement. It may not be a good indicator of how spread out the data actually is. Another way that we can do this is something called the sample mean absolute deviation. We tend to do this for samples and not populations, because with populations there can just be too many data points to deal with. So we tend to look at how far each data point in a sample is from the sample mean for that particular sample. So the sample mean absolute deviation okay, what this tells us is the average distance from each data point from the mean. Okay, so it tells us on average how far each data point is from the mean. And we tend to actually denote it as mean absolute deviation, so MAD. And it is the sum, again I'm going to explain this, it's just a short formula. Okay, it's the sum of the absolute values of the difference between each data point in the sample. So each xi is a different data point in the sample. X bar is the actual sample mean, and n is the number of data points in the sample. Okay, so what are we doing here? Okay, by taking each data point, okay, you can take whatever data points you have in your sample. You're going to take each data point, you're going to subtract its mean of the sample. So let's say I've got 6 data points, I find the mean of those 6 data points. I'm going to take each one of those data points and subtract that sample mean. Then I'm going to take the absolute value of that difference. What that does is it makes that difference between the 2 points positive. Okay? Otherwise, you're going to get some positives and some negatives, but we want to make it a distance. Okay, I want to see the distance between each data point and the mean for that sample. So by taking the absolute value, I make that difference positive because some data points are going to be above the mean and some are below the mean. So all I'm doing is making that difference positive and then adding all of those values together. So I do it for every single data point, and then I add all of those values together, and then I divide by the number of data points that I have in my sample. Okay, so I'm just looking at the mean distance between each data point and the sample mean for that particular sample. Okay, let's look at an example of this. So here I have 5 data points, okay, 3, 12, 20, 15 and 0. And the mean of these 5 data points turns out to be 10. Okay, so what I'm going to do is I'm going to take each one of my data values. So we'll start with the first one. I'm going to take the data value, subtract the mean and find that difference, which in this case for the first one, 3 minus 10 is negative 7. And you're going to do that for each one of our data points. So what I'm doing here for each one is I'm just doing xi, the data point, minus the sample mean. Okay, now you'll notice that some of these are positive and some of these are negative. It depends on whether the data point is below the mean or above the mean. If it's below the mean, you're going to get a negative. Above the mean, you'll get a positive. The reason that we take the absolute value is if you go down this list of differences, okay, we have negative 7, 2, 10, 5 and negative 10. What you notice is if you add all of those together without taking the absolute value of each one, you actually get 0. So if I add all of those values together, negative 7, 2, 10, 5 and negative 10, I get 0. They all cancel one another out. Okay, that is because if you think about it, your mean is somewhere around the center with all the data points either side of it. So when you take the difference between the mean and each of these data points, they should all cancel one another out because some are going to be below the mean, some are going to be above the mean, but the distance that they are away from that mean should all cancel each other out when you add those negative and positives together because the mean is a central value for those data points. So this is why we must take the absolute value in order for this to actually mean anything whatsoever. So coming back to our formula, what I'm going to do to get the mean absolute deviation for this sample of 5 points is take those absolute values of each of those, then add them together, and I'll divide by 5 because I have 5 data points. So all you would do is take the absolute value of each one, so make each one of these values positive, so negative 7 becomes 7, then 2 remains the same, 10 remains the same, 5 remains the same, and I'm going to make negative 10 positive as well. And then I would divide by 5. Okay, this is going to come out to, I think, 34 over 5. Okay, now I want to look at, is this a resistant measure? Okay, going back to what we did in 4.1, we looked at whether these were resistant measures. That means if there's an outlier in here, does it significantly impact my value for the mean absolute deviation? Well, if I suddenly have one of these values was a major outlier, okay, it's going to affect my mean, and therefore it's going to make my average deviation from that mean change dramatically. Okay, so I could have, instead of 20 here, if I made that value 70, my mean is going to change significantly, which means that when I plugged it into this formula, my mean absolute deviation is going to change significantly. Okay, because each of my values is going to be significantly different distances from the mean now than it was originally, because I have most of my data clustered around that mean fairly closely. But now with one outlier, my mean changes, and now all of my data points are a different distance from that mean. So this value is going to change dramatically. So this is not resistant to outliers. Okay, it is not a resistant measure. Okay, outliers affect it significantly. Now in statistics, we really don't like to take that absolute value. Okay, it's not really something that statisticians like to use. It's not a function that they like to use. So instead of doing that, what they tend to do is actually square that distance between the data point and the mean. By squaring that, whenever you square a number, remember it would make it positive. Now, yes, it makes it larger, but we are still getting some kind of measurement of a distance, even though it's technically a distance squared, between the data point and the mean. So it's still a measurement of the distance, but of course, the larger the distance, that is now going to be amplified even more because we are squaring it. So whenever you've got a pretty small distance, squaring it isn't going to make too much of a difference. But when you square a large distance between the data point and the mean, this is now going to have a greater effect. Okay, and I'm going to come back to that in a second. But as I said, we don't like to use an absolute value. It's not a function that statisticians like to use. So instead what they use is a squared function. And by doing that, by using the square of the distance, we're actually going to get something called the variance. We're going to do one for the population and one for the sample. So the population variance, again, is just a measurement of how far the data points are from the mean. Just remember that now we are squaring that distance, so the difference is going to be amplified. So we're going to get, for the population variance, it's actually denoted by a lowercase sigma squared. Okay, kind of a weird notation, but that is how we denote the population variance. It's the variance for the population. It's a measurement of how spread out our data points in the population actually are. Okay, so sigma squared is how we denote the population variance, and it is the sum of each of the data points in the population minus the population mean, and then you're going to square that value. So you take each data point individually, you subtract the mean from it. You do this for every single data point, and you square each of those differences. So I take a data point, I subtract the mean, and I square it. I take another data point, I subtract the mean, and I square that value. When I get all of these differences squared, I then add them together, that's the summation, and I divide by the number of data points in my population. Okay. We can also have a sample variance. This one is slightly different, and I'm not going to explain all of this. I've actually put an explanation in my class notes if you would like some more information about this. And I will also explain it in class on Tuesday during our problem session in class on Tuesday when we talk about the homework problems. I'll go a bit more in depth about this, but mathematically it's to do with something called degrees of freedom, which we will come across in our final week in this course. But for now, you just have to remember how to calculate it. The sample variance is denoted by S squared, and it's the sum of each of my data points in the sample minus the sample mean, and then again I square those differences. So I take a data point, I subtract the mean of that sample from that data point, and I square it. And I do this for every single data point, and then I add all of those squared differences together. But this time, I'm going to divide it not just by the number of data points in my sample, but actually by the number of data points minus 1. Okay? So just remember, if you're dealing with a population, this is your formula. You're dividing by the number of data points in your population. If you're dealing with a sample, we're actually going to divide by the number of data points in the sample minus 1. As I said, I will explain more of this in class if you are interested, but for the purposes of this course right now, you just need to know that you divide by the number of data points minus 1. Now, as I said, there's a few issues with this, okay? Number one is either in your sample or in your population. If you have a data point that is an outlier, that is going to greatly impact your variance in either a population or a sample. Because if you have a data point that is an outlier, it is going to be much further away from the mean than all of the other data points. So then when I find the difference between that outlier and the mean, it's going to be vastly different to the differences between each of the other data points and the mean. So you can think of it kind of like on a number line. If the mean is here, and most of your data points are kind of scattered around the mean here, but then you have an outlier over here, okay? The difference between those two values, the mean and that data point, so this is sum xi, and this is your mean. We'll say that it's a sample mean for now. When I do xi minus x bar, that distance is going to be much different than the distance between that data point and the mean, okay? So because of that, not only do we now have to deal with that vastly larger difference, but we are now squaring that value. So outliers greatly impact the variance, because not only do you have that larger distance between the outlier and the mean, you now are squaring that distance, and that enhances that even more. Okay, so it actually has a much greater effect on the variance than any other data point. So because of that, this is not a resistant measure. Okay, it is greatly impacted by outliers. Okay, an outlier is going to seriously make this much, much larger. Okay, that makes sense. Think about what we're actually measuring with the variance. We're seeing how spread out our data is from the mean. Okay, if you've got outliers, that means that you have data points that are really spread out compared to the mean. That means that your variance would be larger. So this makes sense. The more outliers you have and the further away they are from the mean, the larger your variance is going to be, because that distance is squared. So you're going to get a very large variance, which means that you have more variance in your data points. Your data points are more spread out. So the larger the variance, the more spread out your data is. The other problem with the variance is that we have this squared value in there. So it affects our units. Okay, let's say that my data was in feet. Okay, let's say I was measuring height, okay, of something. And so my data points were in feet. That means, let's just go with the sample variance here. That would mean that this data point xi, its unit would be in feet. The mean would also be in feet, okay? because I'm just taking a central point for my data. Okay, so my mean would also be measured in feet. So when I take a data point measured in feet minus something else in feet, the result of this is also going to be in feet. It's like saying that something's 5 feet and I take 2 feet away from it, I'm left with 3 feet. Okay, so I'm still measuring in feet, but now I have this exponent. So I am now in different units to what I started in. My data was in feet, but my variance is in square feet. This does not affect the unit whatsoever. I'm just dividing by a number. Okay, I'm dividing by a scalar that has no units. So that doesn't affect my units whatsoever. But that exponent does. So you start out in 1 unit, and then your variance is in units squared. Because of that, we really want to get away from it. We would like the units of the variance to be the same as the units that we were in for our data. So how do we solve that issue? Well, that is why we actually labelled each of these as something squared. Okay, the notation for the variance was always sigma squared or s squared. So the reason we do that is because we would now like to square root this whole formula to get a different quantity that we're going to deal with. But that quantity that we are now going to deal with is going to have the same units as my data points. Okay, so if I had my data was in feet, my variance would be in square feet. But now by square rooting my formula, the result that I get will again be back in feet, which is the same as where I started out in my data. If we square root both of those formulas, you actually end up with something called the standard deviation. Okay, so I have a population standard deviation. Standard deviation we tend to just denote by SD whenever we have to write the words down. So population standard deviation is just denoted by sigma, because remember we are taking the square root of our variance. Our variance was denoted by sigma squared because we really like to deal with standard deviation as it's in the same units as our data. So we denote it by sigma, which is the square root of that whole expression. Okay, so I calculate it exactly the same way. I do the exact same calculation as I did for my population variance, and then whatever result I get, the number that I get out, I just square root that, and that gives me my population standard deviation. In the same way, our sample standard deviation is denoted just by s, because remember sample variance was s squared, and that is the square root So again, you figure out what your sample variance is, you get the result for that, and then you just square root that number. It's another measure of dispersion from the mean. It just tells us how far away this data is from the mean. Now it's a weird measurement because of course we're squaring those distances. We're then taking the average of the squared distances, and then we are square rooting that value. So it's kind of a convoluted way of doing this, but it's still a measurement of those distances, okay? It's just not those exact distances. We're doing some stuff to it. But the size of this value will tell us something about how spread out this data is. And this is the particular value that statisticians like to use. Okay, they like the standard deviation because it's in the same units as our original data. Now, again, there's some things that we like about the standard deviation compared to the variance. Okay, number one is that it's got the same units as our original data. The other thing about the standard deviation is that it is always non-zero unless okay, I want to go through a couple of other properties of the standard deviation. The first thing is, so we'll label this properties of the standard deviation, okay, of whatever data set that you have. Okay, the first thing is it's always non-zero. Okay, the only time that you could get a zero standard deviation, so the only time that either one of these formulas would equal zero, is if every term in here was zero. Let's think about that. You're taking some terms that are all positive because you've squared them. So each one of these terms squared is going to be positive, okay? And then you're adding together all of these positive terms, which gives you another positive number. You're then dividing by a positive number, again gives you a positive number, and square rooting it to give you another positive number, okay? So it's always going to be a positive number. The problem is you cannot get zero unless every single one of those terms was zero, okay? Because there's nothing cancelling anything out here because you've got all positive numbers coming out once you square something. So the only way that you can get zero at the end is if each of those differences was zero. That would mean that every single data point equaled the mean, which basically never happens, okay? So the standard deviation is always non-zero unless every single data point is the same. Because then each of those differences would be zero. So then squaring it would be zero, adding them together would be zero, dividing by the number of data points that there are is still zero, square rooting it is still zero. So that's the only way that it can be zero. So it's always non-zero. I've mentioned this with the variance, but it's also true with the standard deviation. It can be dramatically increased by just one outlier. Okay. If you have one outlier in the data, then as I said, that difference is going to be even larger once you've squared it. So it's going to have a greater impact on your variance and therefore a greater impact on your standard deviation. Okay, so one outlier can change the standard deviation a whole lot. And I've already mentioned this before, but it has the same units as the original data. There is a video on standard deviation by Against All Odds. So if you go to the Blackboard page and go to the left-hand menu on the Blackboard page for this course, Again, you'll see the against all odds videos tab, not the video clips, just the videos. If you click on that tab, then there should be, I think it's the third video down, is against all odds inside statistics standard deviation. Okay, it's a video all about standard deviation. So I would highly encourage you to go ahead and watch that. They're given another explanation about standard deviation, and then they also tell you about some real world examples where it would be used. They go slightly more in depth than what we've done so far, so if they kind of lose you with some of it, please don't panic. We will get to it within the next couple of weeks, but it kind of gives you an insight to standard deviation and where we're going with it. Okay, so I would highly encourage you to go ahead and watch that. The next thing I want to look at is something called the empirical rule for symmetric data. Okay. Remember, symmetric data is when I take my frequency distribution for some data, so I've put my data into classes and I've seen how many things fall into a particular class, and then I go ahead and draw a histogram for that data, and I get a histogram that looks like a bell-shaped distribution like that. Okay, it's symmetric. Now also remember, for symmetric data we've said that the mean equals the median equals the mode. Okay, this value here is our mean, it's also our median, it's also our mode. Okay, there's a few other things about symmetric data that are very useful to know, and it is only true for symmetric data, so make sure that you don't use these values for any data that is not symmetric. If you can't get data values that give you a histogram that is symmetric, this does not work. Okay, but what the empirical rule tells you is three things. The first one, and these are rough numbers, these have been rounded, okay, but it tells us how much of the data lies within a certain number of standard deviations from the mean. So the first thing it tells us, and they are random numbers, but you do have to remember them. This is also called the 68, 95, 99.7 rule, because those are the three numbers that you have to remember. But about 68% of the data lies within one standard deviation of the mean. Okay, so let's say that you've got, we'll deal with a population for now, okay, and let's say that your mean is there, okay, whatever that value is, remember it's right down the middle is the value for the mean. Then you figure out what your standard deviation is, which again, if we're dealing with a population, is sigma. Okay, if we were dealing with a sample, it would be S, but I'll deal with sigma for now. If I figure out what my standard deviation is for this particular data set, okay, which tells us how spread out that data is. If I add one standard deviation to the mean and I subtract one standard deviation from the mean, so let's say I do that for whatever that particular value is for sigma. Okay, it's not very well drawn, but hopefully you get the point. It should be symmetric. But if I look at one standard deviation above the mean and one standard deviation below the mean, the amount of data that falls between those two values should be roughly 68% of my whole data set. So I should be able to find 68% of my data values fall within the range mean minus the standard deviation, mean plus the standard deviation. Okay. Second thing you need to know is that about 95% of the data, so roughly 95% of the stuff under the curve, 95% of the data lies within 2 standard deviations of the mean. So if I go ahead and do this again, and I add another standard deviation to the mean, and I subtract another standard deviation from the mean, so now I'm at mu plus 2 sigma and mu minus 2 sigma. So I've subtracted 2 lots of the standard deviation from the mean. I should find that between those 2 values, I have about 95% of my data. Okay. And finally, you pretty much can get all of the data if you go within 3 standard deviations of the mean. So really all you have are outliers outside of 3 standard deviations of the mean. It's very unlikely that you have a lot of data outside of that range, okay? Because if I add 3 standard deviations to the mean and I subtract 3 standard deviations from the mean, I should catch most of my data points between those 2 values. Okay, I catch 99.7% of my data between those 2 values. So again, you can draw that on. And if I had there was mu plus 3 sigma and here was mu minus 3 sigma, between those 2 values, I should have 99.7% of my data. Okay, so I've basically caught almost all of it. It's only the very tail ends that sometimes you don't catch if you go that far out. Okay. Let's go ahead and do a quick example. Okay, I'm just going to write down the numbers to this. If you want to write out the actual question as I say this, then feel free to. It's also in my class notes if you want to go ahead and look at that if you miss any of this. But it says, suppose a group of high-tech stocks have an average earning per share of $6.26. So our stocks have an average earning per share of $6.26. And the standard deviation is $1.37. So the average earnings per share are $6.26. So that is going to be our mean. And I'm going to put this as a population of these stocks, okay? And the standard deviation of those, which is sigma, is $1.37. If the data possesses a bell-shaped distribution, so it's a bell-shaped distribution meaning that it must be symmetric because it has that bell shape, which interval contains 68% of the earnings for those stocks? Okay, so the mean earnings for those stocks was $6.26. The standard deviation for those earnings was $1.37. I want to know what interval contains 68% of the earnings that I could possibly earn from these stocks. Okay, so 68% of the data is caught within 1 standard deviation of the mean. So if I add 1 standard deviation to it and I subtract 1 standard deviation from it, I should incorporate 68% of my data between those 2 values. So if I do $6.26 plus $1.37, I get to $7.63. And if I do the mean minus the standard deviation, I should get to $4.89. So between $4.89 and $7.63, so between those 2 values, we'll take x to be any of our data points between those two values, I should have 68% of my data lies within that range. Okay. Now there is another theorem that we can use when the data is not symmetric. So remember that we can have positively skewed and negatively skewed data where that mean, median and mode aren't necessarily straight down the middle. Okay, and the theorem that we're going to use for that is actually named after someone, and it's called Chebyshev's theorem. Okay, kind of a weird name, but hopefully you can remember that. Hopefully it'll help you remember it. Chebyshev's theorem. It's when the distribution is not normal. We'll use that word normal later on. It hasn't got a normal distribution, but it's when it is not symmetric. Okay, so it can be positively skewed or negatively skewed. It can be symmetric, it's just not as accurate as the empirical rule for symmetric data, as you'll see in a second. But what this tells us is the proportion of any data set lying within k standard deviations of the mean is at least this value. What does this tell us? It gives us a lower bound for the amount of data that can be found within a certain number of standard deviations of the mean, okay? So it tells us the smallest possible amount of data that I should find within a certain number of standard deviations from the mean, okay? It can be more than this amount, but you'll get at least this amount. Also note that this only works for k is greater than 1. So we're looking at k standard deviations from the mean. Okay, this formula does not work when k is equal to 1. So we do not have a formula for looking at within 1 standard deviation of the mean when the data is not symmetric. This only works for 2 and above. Okay. But let's look at that. Let's look at within 2 standard deviations of the mean. So what am I doing here? I'm adding 2 standard deviations to the mean and I'm subtracting 2 standard deviations from the mean. So I'm looking, if we're doing populations, I'm looking within this range, okay, between the mean minus 2 standard deviations and the mean plus 2 standard deviations. And I want to see what proportion of my data points lie in that range, the proportion of my data points x that lie in that range, okay. Well, let's go ahead and do that for k is equal to 2. It will be 1 minus 1 over 2 squared, which is 1 minus 1 over 4, which is 3 over 4. Okay, that tells me that 3/4 of my data, or 75% of my data, at least 75% of my data, lies within 2 standard deviations of the mean. For any data set that I have, doesn't necessarily have to be symmetric. Okay, so even if I have something that has a positive or negative skew. So I could have a data set that has a histogram that's got that kind of a shape. Okay, this still works. Within 2 standard deviations of my mean, I will still find 75% of my data points or more data points lie within that range. Okay, at least 75% of my data points lie in that range. Okay, you can do this again for 3 standard deviations. So when k is equal to 3, I will get 1 minus 1 over 3 squared, which is 1 minus 1 over 9, which is 8 over 9, which if you work it out, it's about 88.9%. Okay, so within 3 standard deviations of the mean, I would expect to find at least around 89% of my data. Okay, as I said, this works for symmetric data, but it's not as strict a boundary as we had from the empirical rule. Okay, if we look at 2 standard deviations of the mean, I know for symmetric data that I would get about 95% of my data lies within 2 standard deviations of the mean. What this tells me is that at least 75% of my data does. So it's a much looser lower bound than what I had with the empirical rule. Okay, so it does still work because I've got a lower bound of 75%, and 95% is definitely above 75%, but it's a much looser lower bound. Okay, same goes if we look at 3 standard deviations of the mean. Okay, again, this gives me a lower bound of around 88.9% of my data lies within 3 standard deviations, but I know for symmetric data it's 99.7%. So again, it's a very loose lower bound. So we prefer the empirical rule for symmetric data, and this works well as a lower bound when we don't have symmetric data, when it is skewed in some way. Now I want to look at one more measurement of the spread of data. But everything we've looked at so far with the standard deviation and the variance and our average deviation from the mean, okay, they've all had units. Sometimes statisticians prefer it if we can get rid of all of our units and just get a number, okay, that is a measurement of how spread out our data is. Okay, it's a good way of seeing how spread out the data is, but getting rid of any units. And a good way of doing that is by using something called the coefficient of variation. Again, it's a measure of the spread of data, but this time this one won't have any units. The other reason why we like this is it's very good if you want to compare 2 data sets that maybe have different units. Okay, this is a good measure of the spread of data because it will just give you a value rather than a value that has units attached to it. So if you've got 2 data sets that you want to compare to one another, but they've got entirely different units, this is a good way of seeing, okay, can I compare the spread of one set of data to another set of data? Okay. Now the coefficient of variation, again, depends on whether you're dealing with populations or samples, but it's actually the same formula, the actual notation inside it changes depending on whether it's a population or a sample. It's denoted by CV, and I will write this down and then we can talk about it. Both of these say the same thing, it just depends on whether you've got a population, in which case you're using a population standard deviation and population mean, or if you're dealing with a sample. What this does is it gives the standard deviation as a percentage of the mean. Okay, so the coefficient of variation comes out as a percentage, and it just tells you what percentage the standard deviation is of the mean. So we're taking the standard deviation for the sample or the population and dividing it by the mean, giving us a proportion of the standard deviation to the mean, and then multiplying it by 100. So it's just what percentage the standard deviation is of the mean. So for example, if you had a standard deviation of 1 and a mean of 4, okay, that would tell me that my standard deviation is 25% of the value of my mean. Okay, if my standard deviation was 2 and my mean was 10, that would tell me that my standard deviation is 20% of the value of my mean. Okay, so it just gives me a percentage of the standard deviation with respect to the mean. As I said, we like this because it is unit free. Okay, so you will see it occasionally, and statisticians do like it for that very reason. But we deal a lot with standard deviations as it helps us with different kind of distributions that we're going to use. But just know that this is a great thing in the statistics world because it is unit free. Now I want to look at how we can actually find the standard deviation and variance of a data set without having to go through actually calculating that formula, especially when you have a lot of data points. Using that formula and trying to do this by hand isn't exactly easy, okay, because you have to find the difference between each of those data points and the mean. You then have to square each of those the distances, then you have to sum those squares, then you divide by either the number of things that there are or the number of things minus 1, depending on whether you have a population or a sample, and then if you want the standard deviation, you've got to square root it. That's a lot of math. So your calculator will actually do this for you. So what I have done, if I go into Stat and Edit, what I have actually done here in List 1 is I've created the list that we saw in the first example when we were looking at the mean absolute deviation from the mean. Okay, the 5 data points that we had were 3, 12, 20, 15 and 0. I've put those into List 1. What I'm going to do is actually find the standard deviation and then the variance of each one for this whole data list, okay? So what I'm going to do, let's quit out of that, and I'm going to go to Stat, Calc, and go into one variable stats. Now this is where last time we were looking at finding the mean, finding the median. Okay, we did this under one variable stats. The list that you want to find the standard deviation or variance of goes in to the first one. So the list, okay, is list 1. That's the list, the data list that I want to find the standard deviation of. I want the frequency list to be cleared, okay? Make sure you have nothing in there. The only time that you want a data list in the frequency list is when you want to find a weighted mean. We are not doing that here. We are just finding the standard deviation of a particular data list. Then I'm going to go ahead and calculate. Now, as I said, there's a lot of information on this screen, and some of it we weren't sure of what it actually meant last time. This is where we're going to discover what it actually means. The two values that you are going to need are Sx and sigma x. Okay? Because when you find your sample standard deviation, you divide by n minus 1, the number of data points minus 1. If you have a population, then you would just divide by the number of data points, not the number of data points minus 1. Your calculator doesn't know whether you are looking at a sample or a population. It has no idea what your actual problem is. It's just looking at a data list. So what it does is it finds both the standard deviation if you were looking at a sample, which is Sx. This is your sample standard deviation. So they've calculated this by dividing by n minus 1 before they've square rooted. And sigma x is where they've treated it as a population. So they've treated those 5 data points as a whole population, and they've divided by n and then square rooted. So they've divided by 5 rather than 4, which they've done up here. So Sx is your sample standard deviation. It's the standard deviation of that data list if that data list represented a sample, okay? Sigma x gives you the standard deviation as though your data list were a population, okay? So sigma x is the population standard deviation. Now, whenever you get a question, you have to look at the word problem and decide whether you are looking at a sample of things or a population of things. That's going back to chapter 1. That is why that was useful, because you have to be able to identify in a problem whether you want the sample standard deviation or a population standard deviation. Are you looking at a sample or are you looking at the whole population of something? Okay. So as I said, both of these are standard deviations. It's just a case of whether it's population or sample. If you needed the variance, either the sample variance or the population variance, you would take whichever one of these values, either sample or population, and you would square it, okay? If I take the square root of the variance and get the standard deviation, if I square the standard deviation, I should get the variance. So that's exactly what I'm going to do here. If I wanted the sample variance, if I had a sample of something and that's what those data points represented, and I wanted their variance, I would square this value, this 8.33. If I wanted a population variance, because my data points represented a population of something, I would square this value, okay? So it all depends whether you are looking at a sample or a population, but your calculator will automatically calculate that standard deviation for you by just going to stat, calc, one variable stats, and then running one variable stats on that data list. Okay. So you always know where to find the mean, the standard deviation, the median is down here. You've got your upper and lower quartiles. It tells you the number of data points and you get your maximum and minimum data values. So this is a very, very important screen. It tells you a lot of stuff about that data list. So keep that in mind as you do your homework. If it gives you a list of data and says, find the standard deviation of this list, where this list represents a sample, you know that you are looking at Sx. If you've got to find the standard deviation of a list of data where that list of data represents a population, you know you're looking for sigma x. And if it asks for either the sample or the population variance, all you're going to do is just square the sample standard deviation or the population standard deviation, and that will give you the associated variance.